So welcome to the HKS Energy Policy Seminar. I'm Joe Alding, and I'll serve as the host for our seminar today. As a reminder, we are in a hybrid format, convening here in the David Elwood Democracy Lab in person, as well as having friends and colleagues joining us via Zoom. So welcome to our friends on Zoom. It's my pleasure to welcome Andrew Waxman for his talk, Measuring Air Pollution Co-Benefits of Carbon Capture, Utilization, and Storage Technology. Andrew is an assistant professor at the Lyndon B. Johnson School of Public Affairs at the University of Texas at Austin, and a visiting scholar at the Belfer Center's Environment and Natural Resources Program and Science, Technology, and Public Policy Program. He's an applied microeconomist examining the relationship between environmental outcomes, urban policies, and inequality. He was previously on the faculty at Arizona State University and affiliated with the Cornell Institute for China Economic Research. Professor Waxman earned his doctorate in applied economics and management from Cornell University. Andrew, we've had fun having you in the audience, joining us over the course of this year in the Energy Policy Seminar, and thrilled to have you now as a speaker. Welcome to the seminar.
Thanks, Joe. Thanks very much for the opportunity to speak here, and thanks to the Belfer Center for having me for the year. So today I'm going to talk to you about what I've been working on primarily while I've been here, which is thinking about some of the economic implications of largely air pollution co-benefits associated with carbon capture technology, with largely a focus in the United States. But I'm going to do a sort of a big retrospective or overview from the beginning. I just want to acknowledge this is part of a larger project that's supported by the Alfred P. Sloan Foundation associated with the economics of CCUS. I'll be saying CCUS is a shorthand for carbon capture, utilization, and storage technology. So thanks to them. All right, so big picture here, I'm going to talk about some general things about CCUS technology, thinking a little bit about policy implications about current US federal policy associated with CCUS. Then I'm going to zoom into a specific project that I'm working on here on these co-benefits. But before I do either of those things, let me just give a caveat, which is that as Joe kindly introduced me, I'm an applied economist. So I will be discussing some of the technological implications, some of the engineering, even a little bit of geology, but those are not my expertise. And so I'm not going to claim to be a big expert on them, more on the economics. And second of all, this is neither a pro nor an anti-CCUS talk. I think people tend to get strong feelings associated with this. I think there are reasons to think that this is important. I'll talk about in a second. There are also some challenges associated with it. And that's the context of which I'm giving this talk. All right, so as some motivation, make sure this is working. Yeah, so this is from the International Energy Administration's net zero scenarios. So this is for end of century net zero pathways. And as part of their core motivation, you can think about different things that would get us from sort of the business as usual in yellow up here down to something approximating zero emissions by the end of the century. And a big part of that, according to them, is in red here, big as in at least 9%. And this is worldwide, right? So the IEA makes very clear in their scenarios that without carbon capture technology, with being at least a part of the solutions, not necessarily the majority, but a part of the solutions, decarbonization, world decarbonization may be much more expensive, not necessarily impossible, but much more expensive than it would otherwise be. Why expensive? Well, one way to think about this is in terms of emissions. And here I'm talking about greenhouse gas emissions. And for most of this talk, I'm really thinking about CO2 emissions, carbon dioxide emissions. We can think about investments in electricity, grid, transmission, renewables that might reduce the CO2 emissions and decarbonize our economy. But there are a series of harder to reduce emissions, particularly from industry, things for which we have some ideas. We could electrify certain processes. We could use alternative fuel sources like hydrogen. We could even use alternative inputs, feedstocks into those processes. And also a big part of this is what's called load following electricity. This is a number of things, but one way to think about this is that when we get really hot or cold temperature changes, we need to increase our electricity production. This can be challenging. Maybe during the Q&A, we can dive into that in a little bit more detail and what the implications are for that CCUS. But all that's to say is that there's a meaningful portion of greenhouse gas emissions that might be challenging and or expensive to try and abate. Doesn't mean we shouldn't do it, but it means thinking about a patchwork of technologies or policies that could help make that happen. This is a very hard to read chart from the fifth assessment report of the International Panel on Climate Change. I will just give you the big picture summary of what this chart is trying to say, which is about essentially from their set of models for, again, reducing emissions by a set time period. And here it's thinking about 2015 to end of century. They point to scenarios in which there is no CCUS as having substantial cost increases in what it will cost society or the world to try and get to net zero without CCUS. In fact, only 4 of the models, and I think there's at least 12 of them. Actually, I think there's in some cases more. Only 4 of the models are actually able to hit that by end of century without CCUS. So it's challenging, I guess, is the story. You can see for industrial emissions specifically, which is what this is worldwide, that IEA report points to 29% of industrial emissions being addressed by 2050 from CCUS to meet decarbonization goals. These would vary depending upon whether we're talking about the US or talking about China, because our energy sectors, our industrial processes, and our fuel sources and the cost of energy are quite different. So in the United States, they would project something like 23% coming from CCUS, but also about 24% in China. So an important part of the story in both countries, potentially. This is from a report that came out, I think, just last week from Bloomberg New Energy Finance. They're also kind of private sector energy modelers. But here they're just collecting data on global investment in carbon capture and storage, or CCUS, by region. So the blue here is lumping together Europe and the Middle East. The purple is in the Americas, North and South and Central, and then Asia Pacific in green. And you can see a substantial increase, although 2020 was kind of a boon year for a number of reasons, in both sort of European and Middle Eastern investments in CCUS, as well as in the United States, with Asia also substantially investing in this technology. So it's definitely something for which investments are on the rise. One question, I really haven't pinned this down, is what are the right things to use CCUS technology on? This is not the focus of this talk, but it's going to be relevant for the scenarios that I talk about in a few minutes. One thing here is that the cost of doing carbon capture, so here we're thinking about we have a point source, something like a power plant, a fossil fuel power plant, or an industrial location like a petrochemical facility or a gas processing plant. You want to capture that CO2. Well, the cost of doing it is inversely proportional to the purity of the CO2 stream, right? So something like fossil fuel combustion as part of electricity generation, it does not necessarily generate the purest stream of CO2. And so it can be quite expensive using conventional technologies. There's all sorts of work being done to try and come up with new fossil fuel combustion technologies that will more efficiently produce pure streams of CO2. And actually, we'll talk about that a little bit on the back end of my talk. To some people's minds, using CCUS on coal and natural gas-fired power plants in the US could be justified as a kind of bridge until full use of renewables as well as electricity storage is feasible. Others think that this is kind of locking in fossil fuel technology for longer than it may otherwise do. I'm not going to take a stance in that debate, but I think it's an important one to have. The case for CCUS for industrial emissions is a little bit clearer, which is to say, again, if you want to try and hit ambitious decarbonization goals, so reduce emissions quickly, the set of alternatives other than CCUS for a set of large CO2 producing industries is relatively small. We have relatively few options. And this is important because in the United States, as electricity generation CO2 footprint has been declining, for industry, it's remained largely flat. And in fact, in the context of the shale boom, where natural gas prices had been going down over the last decade, actually industrial facilities to some extent had increased their emissions as a result, as that sector in the United States economy grew. This is happening in the context of a decrease in electricity generation in the United States from coal, but an increase from natural gas, and nuclear remaining sort of flat. I won't get into retirement or new facilities on that, but that's an interesting topic as well. And then a growing share of renewables. This will become relevant when I talk a little bit about the co-benefits, but this is the retirement of existing coal-fired power plants in the United States. So one of the big stories about reduction in CO2 emissions from the power sector in the United States is moving transmission not just to renewables, but also from coal towards natural gas. Per BTU or megawatt hour, coal produces a lot more CO2 than natural gas does. Obviously, just moving to natural gas is not going to get you all the way to decarbonization goals, but it is a big part of the story in the United States about what this has meant up to now and probably in the near future. So I'm going to talk a little bit about the key federal incentive that the United States uses to try and encourage CCUS investment, and some thoughts about the economics associated with this. So the current federal tax incentives are a production tax credit, but it's a little bit different than production tax credits work, say, in the renewables sector. The 45Q incentive currently for geologically stored CO2 emissions, that is to say, those that are not being used for oil recovery, I'll talk more about those in a second, return a tax credit of $85 per ton. This is increased as part of the Inflation Reduction Act passed the other year. And it varies a little bit depending upon some conditions. I'll show that in a second. In theory, taxes, when we teach this in sort of introductory microeconomics or even environmental economics classes, we sort of show the equivalence of environmental taxes and subsidies for a given a ton of CO2 reduced. A tax of, say, the social cost of carbon or some proportion of it would induce the same reduction in emissions as an equivalent subsidy, right? But that's not necessarily the case, as has been shown, for a long time now, when we think at the industry level. Because if you think about a firm that was just barely profitable, under a carbon tax, it may be induced to exit the industry, to close down, whereas under a subsidy, it may be fully operational, right? And this has interesting implications in the context of thinking about CCUS for fossil fuels or industry vis-a-vis renewables, right? Because part of the argument about incentives for renewables in the United States is that it had been a nascent industry and we wanted to grow the size of that industry. And so these would be temporary incentives which would help to get them off the ground. It's a slightly different story maybe when we're increasing the size of this share of industrial and fossil fuel generation production as a result of producing it this way. And also, if you think about two facilities, you may have this on the next slide, but I'll just go ahead and do it again, or do it already. If I have two facilities, one is older and maybe produces more CO2 for the same amount of electricity, and the other one is newer and produces less. Given the same federal credit, I might be incentivized to direct more electricity towards the older, less efficient one in order to capture more CO2 and therefore earn more credit. But there's a lot of sort of interesting details in this. So the current IRA provision varies depending upon whether you meet, say, certain wage and apprenticeship requirements. It varies depending upon whether that CO2 is used versus stored. And one, sort of the most common way in the United States of storing CO2 is by using it for enhanced oil recovery. So these are wells. We've been doing this now for decades. Wells where you have oil that is difficult to get to. And so you use CO2, you pump it down into the well in order to help extract that more difficult to reach oil. The combination of a geological storage credit as well as an EOR credit has actually been a long-standing part of the 45Q program or credit since it's been in existence. And it also is part of probably the reason that this is kind of touted as bipartisan climate policy, because you got both a credit that incentivizes kind of decarbonizing in some sense, as well as one that helps remove oil to be sold on the market. There's also a big incentive for direct air capture. We had a talk last semester about direct air capture and its implications. I'm not going to talk too much about direct air capture during this talk, but the size of that credit is quite large, and some people are hopeful that that will help to move the needle on where we're going with direct air capture technology in the US. One of the things that we're doing in work with the graduate students to try and think, as economists love to do, about alternative policies relative to what we're doing really right now and what opportunities that might leave open. I mean, one of the challenges is if we take away the federal tax credit for CCUS, with the exception of maybe enhanced oil recovery, the question becomes, what do carbon capture firms do if they're no longer federally incentivized to capture that CO2? Can they just vent it back up into the atmosphere? Is there economic uses that we can use for it? And so, one of the classic things is to think about something like a carbon tax or a cap and trade regime that sets a price. The price could be at the social cost of carbon or something higher or lower, and compare that to the current subsidies or alternative subsidies in terms of what the impacts are in terms of firm behavior. So one aspect of thinking about CCUS. So now I'm going to zoom in to a particular project. This is the sort of title of this talk, which is thinking about the air pollution co-benefits of carbon capture technology. So thinking about not just the CO2 that we can potentially put underground to avoid damages from climate change in the future, but also the local air pollutants, criteria air pollutants, as well as those that are precursors for criteria air pollutants, like particulate matter, and what the implications of converting facilities to CCUS would do to those. A lot has been said about the potential climate benefits from this technology. Less is known about the co-benefits. And one of the questions we're going to be interested in asking here is a kind of very simple counterfactual. The electricity sector is a little bit more complicated because if we think about what happens to CCUS, it kind of depends upon what a CCUS power plant replaces. Is it replacing solar power? Is it replacing non-CCUS power? We're going to focus to start with just on industrial facilities. Number one, because as I said, these comprise a major part of sort of hard to decarbonize industry. And also because once they're converted, you would presume that they will be producing whatever they had been, at a comparable capacity. It won't be dependent upon how they're responding to dispatch in electricity markets. And lastly, we're going to be interested in how the cost and benefits, the co-benefits, are distributed across populations living in areas that are affected by the local air pollutants nearby. This topic of co-benefits is a sort of long-standing field of research and policy analysis in looking at environmental regulations. So Joe himself has done work looking at the regulatory impact analysis and implications of looking at those for co-benefits of climate policies and CO2 reductions. Other work has pointed to various CO2 policies, some related to CCUS, some not, and found in some cases cleaning up the air in terms of the mortality impacts, the benefits can be larger than the climate benefits. So we'll speak to that a little bit in my talk as well. So this is why we might care about co-benefits relative to CO2, again, because particulate matter and other air pollutants can have significant respiratory health effects, as well as cognitive and cardiovascular health effects. Reducing their concentration in the atmosphere may generate, in present value or in current terms, substantial benefits. So the data we're going to bring to bear on this is going to be focused on the US Gulf region. We actually expand this analysis, so I'll give you a snapshot of towards the end, focusing around a set of clusters, industrial clusters. This builds on previous work that I'd done with my co-authors, which was looking at build out of industrial expansion along these clusters in the Gulf. This is in Texas and Louisiana, and trying to think about what climate or carbon policy might be appropriate for those facilities. They comprise a set of different industrial processes. These are focusing on subsectors for which CCUS has been demonstrated as feasible. Economically feasible is a different question, but in a separate work, we actually model, given the implied costs from engineering estimates, what federal incentives would induce. And we combine this with emissions data to get a sense of what their local air pollution impacts are. This is both from the EPA's National Emissions Inventory as well as the Continuing Emissions Monitoring System. What we're going to do is match these with an integrated assessment model that's going to tell us from the smokestacks from which these emissions come from, how do those translate into concentrations of pollutants distributed across counties in the United States? And to do that, you need a set of what are called source receptor dispersion matrices. It basically says if I go from one county to another, given the set of emissions that are happening around the country and controlling for prevailing weather patterns, and controlling for all of the other sources of pollutants that you're going to get both in the background and from other point and non-point sources, what does the concentration of pollutants look like? This is what we're going to use, as I'll describe in more detail, is called a reduced complexity model. So you take a very complicated air transport model that you would need to run on a supercomputer, and you make an approximation to it. These have been used now for over a decade in sort of applied policy work, and people have shown that at a first approximation, they do a decent job of giving you what you might get out of one of those more sophisticated models. We combine this with weather data and demographic data that's going to help us describe the populations who might be affected by these concentrations. Okay, so let me give you a little bit more detail about what this essentially implies. So think about a power plant. A power plant, particularly one producing coal, might generate SO2. SO2 is a regulated criteria pollutant. It has important health impacts. But also, there's a whole air chemistry thing that's going to go on when SO2 goes into the atmosphere. And a key implication of this is that it can result in the production of secondary particulate matter here through its conversion into SO4 and contingent on weather patterns. So what this reduced complexity model is going to help to tell me is how, for a different set of emissions of criteria regulated pollutants, how this translates into secondary PM levels at different locations across the United States. Why the focus on PM and not other regulated pollutants? PM generally is found to have the largest health impacts and therefore monetized impacts. That's not to say that these other pollutants aren't important, but this is an important part of the model. Another precursor for secondary PM is NH3. NH3 is ammonia. This can come from agricultural processes, but one of the important things for analysis that I'll describe in more detail in a minute is that the most shovel-ready, technologically ready technology for post-combustion carbon capture technology is something called an amine solvent. So the idea here is if you're going to capture CO2 emissions from, say, a power plant or certain types of industrial processes, the flue gas that comes out, right, so whatever you're burning, whatever comes out of that, you maybe remove some of the impurities that are in that gas, but otherwise you got a stream of CO2 with other stuff in it. You run it through a chemical tower, which is like a several story tall tower. If you kind of go out areas outside of Philadelphia, New Jersey, you can see these things when you're driving down the highway. There's a lot of them along the Gulf in Texas. In that tower is an amine-based solvent. It's nitrogen-based solvent. And what that does is basically capture or help to bind with the CO2. That solvent with the CO2 then goes to a regeneration unit that basically pulls out a pure stream of CO2 that can then be transported and stored. One of the challenges of that conventional carbon capture technology is that it contains nitrogen and it degrades that solvent and produces pretty substantial levels of ammonia in the atmosphere. So one of the interesting things about CO2 is that you may reduce some pollutants that have huge impacts on human health, which are a great co-benefit of doing CCUS. It may be comparable to the benefits from CO2 reduction, but you may also produce other pollutants as a byproduct that could have negative health impacts. So it's not immediately clear without doing the analysis which of these is more important. And that's the goal today. So the model we're going to do is actually going to do that sort of exercise across a large set of facilities, controlling for background pollution levels from other processes like agriculture, controlling for weather patterns, and trying to account for this chemical process that I've described that forms secondary particulate matter. And it's going to do this in a kind of a loop to basically get a steady state of concentrations across the United States. So I've given you the first parts of this model. Basically, I collect baseline emissions. We're then going to predict counterfactual emissions under CCUS. Our baseline estimates are going to use engineering estimates of what the emission factors, what the pre versus post pollution impacts are. For most of the pollutants that we're going to think about, things like NOx, PM, SO2, the pollution levels may decrease. For ammonia, for post-combustion sources, they're going to increase, as I mentioned earlier. We're also going to include some industrial sources for which pre-combustion CCUS, where you basically burn the fuel ahead of time, and then you get a kind of product, and then you use that to produce your industrial process. Those are not going to generate the same level of ammonia, right? So again, this is going to complicate some of the story. We also validate these emission factors using observed emissions from existing CCUS projects, but there's not that many in the United States. There's only about 13 active operational commercial CCUS projects in the United States. So we do it as a validation exercise, but rely on the engineering estimates. The model then allows us to aggregate these to the county level and then run them through a source receptor model that does that translation from emissions to concentrations across county in the United States. We're going to use for our baseline results here the AP3 model, which was developed by Nick Muller, who's a researcher at Carnegie Mellon. We're going to validate those and particularly apply them using a different model called InMap, developed by Jonathan Tessum and his team at the University of Washington to do some environmental justice type analysis. And then sort of the economics comes in here. This is going to help predict changes in concentrations in response. So it's going to basically, based on this sort of counterfactual CCUS outcome, with those new concentrations, we can calculate mortality impacts by effectively taking the change in the amount of secondary PM, using a dose response function, which tells us how mortality at the county level, contingent on baseline mortality and population level, responds to changes in the particulate matters. And then perhaps the most controversial number of all, the value of statistical life, we use that to put those mortality impacts, deaths in effect, into dollar terms in order to compare them with the CO2 benefits you would get from capturing all the CO2. So that's what's behind the hood on this model. We can go into more detail during the Q&A, but it just gives you an overview. One thing before proceeding is just to sort of pin down what the counterfactual is. So for the set of facilities we're going to look at here, and primarily for our main results industrial, we're going to do what economists don't really like to do, which is just sort of wave a magic wand and say, what if all of these facilities were CCUS? That obviously involves a large amount of cost. They're not CCUS right now for a reason. So that's a little bit tricky. The sort of better way to do that would be to basically ask, well, under current federal incentives or even a higher incentive, which facilities would opt in versus out? We have prior work that kind of does that. We estimate a kind of marginal abatement cost curve. And so in some of the extensions of what we're doing, we actually just look at a subset of facilities that were included in that analysis. This is really important work. And there's another team that, for example, at Resources for the Future is doing this with electricity generating units with fossil fuel fired power plants, running a whole electricity sector model. But it's going to be doing that to a rigorous extent is going to be a little bit out of the scope of this model. What we are going to do is compare the costs and benefits we get from industrial facilities to those from a set of electricity generation units that are in the same set of clusters. So these are coal-fired power plants and natural gas combined cycle power plants that are in the same set of clusters to give us a sense of just, if those are CCUS, how would they compare in terms of their benefits and costs? All right, so there's a lot going on here. Let me just give you a general overview. So this is looking from industrial sources in our data. The little polygons here you can see across these maps for 5 states around the Gulf. So Texas, Louisiana, Mississippi, Arkansas, and Oklahoma. These are counties. So this is what this integrated model basically gives us changes in concentrations of pollutants across counties. And this is after the model runs, a graph of the concentrations of ammonia, NOx, so nitrous oxides, particulate matter, 2.5 microns and smaller, and volatile organic compounds, and then an SO2 after the model runs. The PM here is going to include both the secondary PM produced by all these other pollutants that come out of the model, and actually it will also potentially also include some primary particulate matter that comes directly from facilities. And so redder colors are going to indicate increases in concentrations of these pollutants. Bluer colors are going to indicate decreases. So one of the big picture things here is that you see, decreases in SO2, increases in ammonia, some increases in NOx, and then increases or decreases in PM depending upon where we're talking about. That reflects the fact that reducing some pollutants is going to reduce the formation of secondary PM, but increasing ammonia, as I mentioned earlier, could potentially increase the concentration particularly in counties that are located very proximate to high ammonia emitters. We do the same kind of exercise from electricity generation units, so coal-fired and natural gas-fired power plants, again, in the Gulf region. And one of the big pictures here is this is particularly driven by the coal plants, and there's only actually 3 of them, but they have a big impact on our sample. They result in a big reduction in SO2. That's going to have big health impacts, as I'll show later. Increases in ammonia, particularly from the natural gas plants. Some increases in NOx, again, from the gas plants, and then mixed positive and negative impacts in terms of particulate matter. Again, balancing reductions in emissions from some of these with increases in ammonia. All right, so this is taking all of those results together for industrial and electricity generating unit facilities and asking, what does the model tell us in terms of net damages? Again here, greener colors are going to indicate negative damages, which are benefits. So green is going to be a kind of benefit, a reduction in deaths. And so these are the dollar values in millions for reductions in benefits. And so overall for EGUs, you find reductions. This is going to be primarily driven by those 3 coal-fired power plants, which I'll come back to later in the talk. As I'll describe in a second, the natural gas plants actually generate some damages. And then for industrial facilities, it's a mix. In some areas, particularly around Houston, where there's a large concentration of industrial facilities, you actually find an increase in damages. In other areas that are further away, you actually find a reduction in damages because pollution levels further away are actually improved. I think I'm going to skip over this for time, but we can look at the distribution of these based upon where each of these facilities are located. So these are the damages across all the industrial facilities in our data, which again vary depending primarily whether these are pre versus post-combustion. CCUS is the most applicable for this particular process. So things like fertilizer are going to be pre-combustion, other things will be post. And then these are the set of electricity generating units. Here are the 3 coal plants that generate net benefits. And in some cases, the natural gas facilities, again, generate net costs, net damages, again, because they're producing a lot of ammonia if they were to be retrofitted. So the big headline numbers here is that you get in total, if you were to convert all these facilities to CCUS, you would get $1.5 billion reduction in damages, with most of that coming from just removing these 3 coal-fired power plants. Come back to that in a second. Net benefits from industrial CCUS, but for natural gas, again, using conventional amine technology would result in an increase in damages, again, from the production of ammonia relative to reduction in emissions from other sources. So here's the exercise that I said I was going to do at the beginning, which is comparing the net damages from conversion to CCUS in terms of local air pollutants to the CO2 benefits. Now, the trick with valuing CO2 benefits is you've got to pick a social cost of carbon. And we're in an interesting point in time right now where we are reevaluating in the United States what the right social cost of carbon is. So these are the 3 values that are from the Obama administration official guidance brought to 2019, when we're sort of doing the counterfactual analysis. And the percentages here reflect the assumed social discount rate. So this is another huge piece of the pie here is how do we assume society values future costs and benefits to individuals. And then here I've got higher estimates of the social cost of carbon based on lower discount rates that come from more recent draft proposed social cost of carbon estimates from the EPA. And actually, Jim Stock, who's not here, has a recent paper that actually has also quite large social cost of carbon estimates. So if you see, so the thing to keep in mind here is that these are going to be ratios and levels, and so this is going to tell us the benefits from a reduction relative in pollution relative to the benefits from CO2. So for small values of the social cost of carbon, particularly for coal, these co-benefits are more than an order of magnitude larger, right? If we increase the social cost of carbon, the ratio becomes smaller, right? So it's more like a quarter. The co-benefits from coal are more like a quarter of the total benefits. But from industrial and natural gas sources, they can still be 5 to 10% of CO2 benefits from reducing CO2 emissions. So still a very meaningful proportion of total benefits when we compare them to CO2 reduction, although it depends upon the level of the social cost of carbon that we want to use. So last thing that we want to do here is to look at the environmental justice implications of this. So this is a very limited exploration of the environmental justice implications. There's a lot more interesting work both in and outside of economics, trying to think about how do we think about the distributional impacts of who benefits and who is harmed by both climate change as well as environmental pollution. Here we're going to do something much more simple, which is to just look at the set of damages that I produced and correlate those with county level, and actually for what I'm going to show you today, census block group level attributes. So things like the demographics of those, as well as pre-existing exposure to pollution. To do this, we actually need to use a separate integrated assessment model, one called INMAP. This produces more granular concentration estimates at the census block level, which is, again, kind of like a block rather than at a county level. The reason for this is that a lot of the research in environmental economics associated with environmental justice has shown something called the ecological fallacy, which is basically if you aggregate costs and benefits to a large geographical unit, you may miss a lot of the important variation that's going on within that unit. And so in order to try and address this, we look at these damages at a census block group and correlate those with census block group benefits and costs. So these are, as I said before, from the INMAP model, that we validate the aggregate INMAP costs and benefits relative to what our AP3 model that I showed you the estimates from earlier. And these are just a simple regression. These are not causal. These are just correlative of looking at the relative damages or costs from industrial, coal, and natural gas facilities. And just remember that in aggregate, the net damages were negative for industrial and coal sources. So these are going to be a negative number, and positive from natural gas. And we're correlating those with a set of controls, things including for a census block group, the percentage of minority households, those in linguistic isolation, as well as exposure to pre-existing pollution, things like exposure to nearby traffic, diesel particulate matter, whether the houses there were built pre-1960, which would indicate they would have a high proportion of lead paint in the way that they were painted. And we find a positive correlation between net benefits and percentage minority. From low income, sort of the estimates sort of vary and are relatively close to zero. And for other pre-existing sources of pollution, we find high correlation between reductions in damages and pre-existing exposure to those. So sort of mixed evidence in terms of the environmental justice implications, but we're hoping to expand this in a follow-up work potentially to look more broadly at environmental justice. And one point just to make here more broadly is that this is a very narrow description of the environmental justice implications. There are broader concerns about the relationship between frontline communities and these facilities, and other sources of pollution like toxic releases or carcinogens that come from the nitrosamines, for example, that also are produced by amines. So this is just a single snapshot. Also in the work, we look at what happens expanding this to all industrial facilities that are in the same sectors as our sample across the United States, as well as looking at a sort of new technology that hasn't been used commercially yet, but is being built by a firm called Net Power right now in the Permian Basin. They have a demonstration facility that's already proved itself in the Houston area, which produces emissions-free electricity. So it's an alternative to the combined cycle natural gas combustion used in normal natural gas facilities that doesn't produce any emissions nearby. And as a result, you wouldn't get the set of amine emissions of natural gas that we model in our main results. So in conclusion, we find large net benefits from coal reduction. One of the big implications of this, though, is if we just converted that electricity generation that is already kind of happening in the background of the US economy from coal to natural gas, you may already get some of these benefits that I'm describing. But I would contrast that with CCUS using conventional technology would result in about $500,000 damages from natural gas, again, because of the impact of amines, and net benefits from industrial conversion in terms of co-benefits. In the paper, we spent a lot of time trying to understand sensitivity of these to a source of factors like the set of parameters we pick and emissions factors. As I described before, we compare the results to an alternative model, and we spend a little bit more time drilling out those environmental justice impacts that I described to you just now. So, as I said before, these air pollution damages or benefits are only one of the potential EJ impacts. And also, I've touched on one technology application that could improve, for example, the damages that you get from natural gas facilities, the alum cycle natural gas. There are a whole host of other technologies, including some people in this room are working on, that could also reduce the potential emissions impacts of degradation of amine solvents from conventional post-combustion CCUS. So I'll stop there. This is actually our part of our research team in front of the carbon capture facility at the University of Texas campus, as well as looking at cores from the team at University of Texas that does storage. So thanks very much for your attention, and look forward to questions.
Thank you, Andrew. I'll pass around the mic for questions in a moment, but I'll take advantage of this opportunity to ask one of you. So you do this analysis to say, what happens if we just sort of wave the magic wand, as you said? It'd be useful if you could put this in a little bit more the sort of the policy context. And I'm thinking here, because you're focusing on co-benefits, the sort of Clean Air Act lens, which is if we're going to be implementing policies, let's say that drive, like we're doing through the tax code to subsidize CCUS technology, to drive some of these conversions, and we see some pollutants increase, what might that trigger to tackle, say, the ammonia problem? What might that trigger under the Clean Air Act that help us think through whether that might stop the investment from occurring in the first place, or whether it creates an opportunity through that policy tool to try to reduce those, I guess, negative co-benefits / air pollution damages that are associated with the natural gas power plant conversion using this technology you studied?
So, so it's absolutely spot on. So the criteria pollutants that I'm describing that are causing health costs and benefits in their reduction or increase, these are regulated, and so the EPA has regs for keeping counties in compliance with these regulations. Particularly for power plants, for NOx, those regulations are under review, I think, as we speak. So we're hoping that this research we've been in touch with Dave Evans and others at EPA to have a conversation about what the implications of those are. I think the answer is I don't know how the regs will be enforced to try and deal with that, but I think the Department of Energy and the EPA are both thinking about how to enforce regulations that help protect human health in a way that wouldn't necessarily forestall this technology. So I guess the short answer is sort of TBD, but I think it's an important question that the feds are looking at for sure.
Okay, thanks.
So thank you. I find this all interesting and provocative. I'm always confused, however, about something which I hope you can explain. So I want to make a very simple technological assumption, which is I have a plant that's emitting, let's pick sulfur and CO2. And that's all it does. It produces something highly useful, but in terms of pollutants, those two things. And then I can have vacuum cleaners. One vacuum cleaner is a Leontief fixed coefficient vacuum cleaner, and it sucks CO2 and SO2 out of the emissions that are coming out. And the other is a completely separable vacuum cleaner, so you can either suck CO2 or you can suck SO2 or both, whatever you choose independently. And it seems to me that that matters when I'm thinking about what I should be doing and how I should be pricing and regulating, but I'm not sure how it fits into the story here. What is the technological assumptions that are embedded in this analysis?
It's an interesting question. As an economist, I'm going to tell you that my answer is not the definitive one on this, but I can tell you what I read from chemical engineering and geological sources, which is actually I think I maybe have a slide related to this. So what we're interested in here is the pore space where you're going to put the CO2, right? Because as a policy, most of what we're thinking about is collecting CO2 from facilities. So maybe that's the CO2 and the SO2 you were describing. And we want to put the CO2 into this pore space here. You really don't want to do that as combined CO2 and SO2. You want a pure stream of CO2 for a variety of reasons. And so you want that vacuum that can separate the two. The vacuum itself is very expensive, and the firm that's doing the vacuuming is basically going to want to try and deal with the SO2, the sulfur first, and then get the CO2. And what's kind of interesting, I sort of skipped over, is if firms are committing to employing CCUS technology, they're basically committing to using, in many cases, what are sort of conventional, which may be expensive ways of controlling criteria pollutants that the EPA has been working at trying to update power plants and other facilities to do for a long time now. So things like wet filters or systems for scrubbing NOx, for example, right? Those are, in effect, being used right now by post-combustion CCUS facilities in order to deal with these criteria pollutants. So, in effect, the solution that I think is happening is the two-sided vacuum, where one side of the vacuum is done in terms of the CO2 transport and capture, and the other is done by the firm directly in order to make that system work. I'm not sure that was satisfying, but it's the best an economist can do for the moment. Okay.
Hi, so thank you. It was very interesting. On all these co-benefits type studies, there are actually enormous uncertainties in almost every step of the way. And you talked about at the end that you did sensitivity analysis of some of the assumptions. I'm wondering if you can tell us anything more about that, if you have any backup slides or something.
Yeah, great question. So we did sensitivity analysis on several different aspects of these, and a lot of this is sort of influenced by a paper that Nick Muller did in 2000, I think 3 or 4, in looking at uncertainty associated with the AP3 model. One of the challenges, the emissions factors that we use come from the engineering literature, and they don't have a probability distribution associated with them. So we sort of get a midpoint, a high and a low. Other things like the value of statistical life, economists have spent a lot of time fitting probability distributions to. I think the preferred one is a Weibull. And then we can use sort of standard errors associated with some of these other estimates to get a sense of what the probability distribution is. These plots it's a little hard to see maybe from distance, but they're essentially histograms that show the distribution of the net damages. So, 0 is here on that graph and here over here. And so you get a variety of sources. One of the biggest sources, because it's the big number you multiply at the end, is what your choice of the VSL is. The emissions factor is also not a small source of uncertainty either. And one of the challenges is that some of these emissions factors that we're using are from the literature. They're the sort of latest and greatest, but they can be updated. And in some cases, there are newer technologies being used for some of these CCUS processes that may reduce, in some cases, the implied emissions. So the best that we can do is sort of provide a kind of range. I guess my headline story is that you still potentially can get quite large benefits, or even in some cases, quite large damages, depending upon the range of parameters that you're using. For the sort of innovations of this paper, which are largely associated with applying emissions factors as CCUS, they're well within the range of uncertainty from things these models typically try and deal with, like the dose response functions, or just uncertainty in the underlying level of emissions that come from the SEMS or NEI data from the EPA.
Add there's a lot of uncertainty in the atmospheric modeling too, which is very hard to represent in this kind of framework. But yeah, I'm sorry to just have one quick follow-up. You mentioned something about validating your atmospheric model against the other model. Do you do any, did I understand that correctly?
So we validate the main results from the AP3 model against an in-map model, which is just a different reduced complexity. So it possesses similar types of challenges. You're taking a fully forms air transport model and reducing it into something you can run on a laptop. The broad strokes of them are similar. We're trying to, at the moment, basically work out what the differences might be in terms of the two outcomes.
But do either of those models validate against instrumental observations?
Instrumental observations. So, well, that's kind of the trouble with this project, which is that we're simulating large-scale CCUS adoption, which doesn't exist in reality. The engineering estimates themselves essentially come from plant-level impacts. We have collected data for the Petronova facility in Texas, which was a coal plant that briefly operated with CCUS at scale, and for a handful of industrial CCUS facilities, and the order of magnitude of the emissions impacts are comparable to what we have here, but they're not exactly the same. And so, and also, you would ideally want to control for a set of unobservables particular to those specific facilities. So like the Petronova shut down right before COVID, and there was a set of economic factors that was influencing what's going on there. So I think we're able to validate sort of order of magnitude of the impacts. I think there's sort of more research is going to be needed as more CCUS projects come online to basically validate, as you said, with ground level data, essentially what the impacts are. So I think it's an important point. I think we've tried to do what is feasible with the data. I think we need to do more going forward as these facilities come online. Yeah, of course. Thanks.
Hi, thank you for this talk. I think a lot of the current carbon capture projects store the carbon very close, or the CO2 very close to the power plant. But I suppose that across the country, that's not going to be the case because saline formations are dispersed and not always next to a power plant. So I wonder what your assumptions are in terms of the construction of pipelines or the trucking perhaps of CO2 to saline formations, and whether you took that into account in calculating the benefits or the costs of CCUS, and whether that's relevant at all. Perhaps it doesn't have much of a cost or a benefit.
So from a policy perspective, it's definitely very important. The transport costs are not the largest proportion of costs, but they're an important one. As an example, there's a large-scale CCUS pipeline project going through the Midwest right now that's sort of going through both political, legal, and regulatory challenges. And there's existing CCUS transport connected to the Permian Basin and then along the Gulf. We don't include any of the air pollution impacts of transport and storage, largely because those are typically not regulated sources of air pollution impacts, or at least not directly regulated. There's been some work for fracking, looking at the impacts of like fracking trucks on air pollution relative to drilling or uses of the natural gas that's produced from hydrofracking. I think it's an important question. What are the larger environmental or even safety and health impacts of capture and storage and transport? It's sort of outside the scope, in part because our model's not well suited to do it. But I think thinking about where storage and transport happens is a huge part of the policy context for what we're talking about.
Thank you. Apart from the 45Q, right, the market for CO2 has largely been for enhanced oil recovery, right? So, but most of the CO2 that is used for enhanced oil recovery is actually coming from natural sources, meaning it's being produced out of the subsurface just for enhanced oil recovery. So in the same company, you can have, one hand of the company is actually getting or applying for the 45Q tax credits for CCUS. And on the other hand, they're actually buying CO2 and getting it from natural sources just for enhanced oil recovery. So as an economist that works in CCUS, what are your thoughts on how this kind of can be solved?
Yeah, it's an interesting question. I mean, so both of these things are true. So as you said, most of the CO2 that's used for enhanced oil recovery comes from natural sources. And I think actually, yeah, this is this figure basically. So these yellow are naturally sourced CO2 locations and enhanced oil recovery. Some of it is happening in Texas. That said, I think at least up to last year, 11 of the 13 full-scale operational CCUS projects in the United States, their CO2 was used in enhanced oil recovery. So a major part of the story of US operational CCUS is as EOR. And so one policy question is, if we're interested in having greater emissions reductions, will more geological sequestration as opposed to EOR get us further along? Seems possible. As an economist, I would love to see a carbon tax or some sort of comprehensive carbon pricing, because then you wouldn't necessarily need the same level of subsidy to incentivize CCUS. To your question about, oil companies or other firms collecting CO2 from natural sources versus using it from projects, I don't necessarily see a problem in that. As long as the net CO2 is going down from the system that's emitted to the atmosphere. I don't think we're there yet in terms of the national CCUS system, and it would be great to see more, policies of the kind talking about and others that would help to facilitate that. So it's not a hugely satisfying answer to your question, but you're absolutely spot on, and I think there's a lot of different dimensions to this that require economic, policy, technical innovations to try and move the needle. Thank you.
Thanks, Paul. So one thing when we're looking at policy analysis like this, it's interesting to share it with the people who are actually trying to do this stuff and get a sense of what opens their eyes, sort of surprises them, or what may have been without the ability to quantify it, the sense like, oh wait, we kind of knew that was a problem. So, especially when you're at UT Austin, you guys have a lot of engagement with people in the energy industry. And I'm wondering, when you showed these results and showing the difference between coal, which struck me as like, given the fixed cost nature of this technology, that's 3 units, that gets you huge benefits. The sort of large number of facilities in the industrial sector, but you still get positive co-benefits on air pollution. But then when we look at natural gas, sort of similar magnitude, but damages relative to those industrial facilities for natural gas. And I'm wondering, as you've talked to folks who are in the industries, any of this come as a surprise, or some of this they're kind of like, yeah, we kind of knew, but now we've got analysis that starts to make it seem a little bit more concrete?
Yeah, I think it depends upon the room, is the answer to your question. I have given this talk to a room with people in industry, and for example, the ammonia degradation issue that results, amine degradation that results in ammonia, that's a well-known challenge within the industry. It's a well-known challenge within chemical engineering. I think, there may be quibbles a little bit about, kind of which facilities we're talking about and which emissions factors I'm using, which are sort of natural and I welcome those sorts of quibbles. And I think that, regulators are, have been aware of this, as we kind of mentioned earlier. And so I think this is something that both industry and the public sector sort of are aware of. But I think, we're hoping that this helps to encourage more research in this area so that we get, clearer engineering and scientific observations about what's going on. And then also, I think the policy landscape doesn't make clear what the outcome is going to be, how much CCUS, where, what's it going to do, what are the implications and the distributional impacts. And so I think, my hope is that this helps to broaden the conversation.
Great. So before we wrap up, a reminder, you probably all have plans to go to the beach next week. It's spring break. Actually, I know the Kennedy School students, they're going everywhere except for the beach. They have all these treks, places to learn stuff, which is exciting. So we will be off for 2 weeks. We'll reconvene the Monday after spring break. Our colleague, Jim Stock, will be here to talk to us about what's up with natural gas prices, with a specific focus on US LNG. And finally, please join me in thanking Andrew Waxman for his presentation today. Thank you, Andrew. That's great.